So today I'm going to be talking to you about indicator minerals for magmatic sulfide deposits. Namely, I'm going to focus on complexly zoned pyroxenes as a possible new fertility indicator for magmatic nickel-copper sulfide deposits. So the reason we need new fertility indicators is that the Mafic-Ultramafic Intrusions that host these deposits are very common around the world, but very few of them contain sulfides. Even fewer still contain economically viable sulfides. So if we could focus our efforts on more promising targets in the early drilling program, we could save ourselves time and money. So the technique that I'm going to be talking to you about for this talk is X-ray fluorescent mapping. So this gives you both textural and chemical information, and it's great because it requires very little sample preparation. So you only need to cut a flat face on the sample, and you can have a very large sample put into these machines at any one time. They're also quite quick, with thin section size area being scanned in less than an hour, and the full scan range being able to be completed in less than a day. So there's lots of choices when it comes to X-ray fluorescent mapping machines. Most people go with the desktop Brooker Tornadoes or desktop mapping devices. There's also lab-based techniques such as the CSIRO Maya Mapper, which we develop and have in-house, both in Melbourne and Perth. Or we have synchrotrons, which are basically the size of a building. And as you increase the size of your machine, you're getting better resolution, but obviously it costs a little bit more. So doing all of this X-ray fluorescent mapping, we found that complexly zoned pyroxenes were commonly observed in nickel-copper sulfide deposits. So pyroxenes themselves are an extremely common mineral. They're one of the most common minerals in the Earth's crust and occur in lots of these deposits. They have a very wide stability field, which means that they can crystallize in a wide variety of magma compositions. And the zoning that we're going to be looking at today specifically is chromium zonation in pyroxenes. So chromium zonation is extremely slow. Chromium diffusion is extremely slow in pyroxenes. So if you look at this chart, which is a time scale, length scale chart, we have the age of the Earth on this axis and the radius of the Earth on this axis. Everything that plots up in this corner is almost instantaneous, and everything down in the lower corner is extremely slow. And you can see that chrome diffusion in diopside, which is a type of pyroxene, diffuses on the order of microns per thousands to millions of years. So this kind of zonation is robust through geological timescales. So next I'm going to tell you a little bit about zoning patterns that you can see in pyroxenes and other minerals and what they're thought to indicate in the crystallization sequence. So here we have normal zoning, which is a diffuse change from the core to the rim of the crystal, where the compatible elements decrease towards the rims. So chromium, which is compatible in pyroxene, will be very, very low towards the rims, and incompatible elements increase. So here we're looking at a large pyroxene and a titanium chart, and you can see that the titanium concentrations increases towards the rims. So next is sector zoning. So sector zoning is this characteristic bow tie or hourglass shape and is indicative of rapid growth of pyroxene. So this is because pyroxene chromium is more compatible on two of the pyroxene axes as compared to the other one. So when you section the pyroxenes, you get these hourglass or bow tie shapes. Next is we have oscillatory zoning, which is the small scale fluctuations in chromium concentration throughout the crystal, and this represents that we have fluctuating magma conditions. And finally, abrupt zoning, which is an extreme change of chromium content between the cores and the rims. So complexly zoned pyroxene is any combination of sector zoning, abrupt zoning, or oscillatory zoning. And it can tell us a little story of what was going on in the crystallization history. So from this single crystal, which is a clinopyroxene from the Ritke intrusion from the Kotalahti nickel belt in Finland, we can tell from the sector zoning that the clinopyroxene grew very, very rapidly. We can tell from the abrupt zoning that there was a significant change in magma chemistry. And then with the oscillatory zoning in the rims, there were further cyclic changes in the chemistry. So next, I'm going to show you the complexly zoned pyroxenes through mineralized intrusions throughout the world. First, we have Ntaka Hill from Tanzania. So what we're looking at is a stacked XRF image where chromium is in red, iron is in green, and calcium is in blue. So orthopyroxenes show up as orange, olivines show up as green, chromites are very, very bright red, and then clinopyroxenes are usually pink in color. So throughout mineralized intrusions, it's very, very common to see abrupt and sector zoned, both orthopyroxene and clinopyroxene, and then it's common to also see olivine inclusions and fine-scale oscillations. So looking at this example from Ntaka Hill, we have an abrupt change from the cores to the rims, we have oscillations throughout the center, and we actually have sector zoning as well throughout here. Moving on to Jinchuan in China, we can see these orthopyroxenes have significant sector zoning. They have abrupt changes from the cores to the rims, and then these are clinopyroxenes, which also show sector zoning. This is Nova-Bollinger from Australia. So this is a tornado image where everything else I've been showing you has been synchrotron imagery. But you can see that this sample has very large orthopyroxene oikocrysts with small olivine inclusions. And then these oikocrysts themselves have faint sector zoning. Here's the Norilsk deposit from Siberia, and you can see it has an abrupt change from the core to the rim in this clinopyroxene, and it also has oscillations throughout the center, which is difficult to see in this image, but shows up in other color combinations. Finally, we have the Kotalahti nickel belt in Finland, and this is an orthopyroxene that shows abrupt zoning between the cores and the rims and oscillations throughout the rims. So these maps, although they're very pretty to look at, they actually have a lot of data behind them, and you can pull out the concentrations of chromium in these maps. This crystal in particular, which is representative of most of the grains that we looked at, has concentrations between 4,000 and 8,000 ppm of chromium in the cores, which dropped to between 2,000 and 0 ppm chromium in the rims. And this is the abrupt zonation there. So this is a little montage of all of the samples that we looked at, and you can see that the zonations in both clinopyroxenes and orthopyroxenes is very complex throughout these samples. So next we'll look at some barren intrusions, which are from the same regions as these mineralized intrusions, but they are not showing these complicated zonation patterns in their pyroxene. So most of the zonation in the pyroxenes in the barren intrusions are dominated by diffuse or normal zoning, which is the gradual change from the cores to the rims, or no changes at all, such as the Majasari deposit intrusion in the Kotalahti nickel belt. So looking at the data we can pull from this grain, this orthopyroxene, moving from the cores to the rims, you can see that there is a change in chromium concentration, shown in red, but it drops from 6,000 to roughly 3,000 very, very gradually. So this leads us to the question of why there is complexly zoned pyroxenes within the mineralized intrusions. So going back to our example from the Rittkini deposit in Finland, we know that our client pyroxenes were growing very fast. There was a sudden abrupt change in the magma chemistry, and then further changes as well in the chemistry of a smaller scale as this crystal grew. So all that's telling us is that we have an extremely active system. So as we know, it's likely that these mineralized intrusions are formed via conduit systems, which are very active systems. So this is a diagram from Steve's paper that shows this occurring. So we have Mafic-Ultramafic magma coming into these conduits. They're crystallizing olivines and chromites, incorporating the roof and the floor of the conduit, melting the roof, and incorporating silica into the melt, which allows orthopyroxene and clinopyroxene oikocrys to grow, and trapping the olivine, the original olivine that crystallized. And then it flows further through the conduit where the magma chemistry continues to change. And you get these variations in the rims of these pyroxenes. And then as they settle, and during the final solidification, you get normal zonations just towards the rims of the very, very edges of the crystals from normal trapped liquid reactions. So hopefully this can be a useful indicator for these sorts of magmatic sulfide deposits. Most of the images I showed you are from the Australian synchrotron, but you can see these features using normal desktop XRF. And if you know what you're looking for, you could probably convince yourself you can see them in plain polarized light like I have. Admittedly, our desktop XRF is probably a little bit out of date, and the technology has increased a lot in the last few years. So if you had a more recent model of desktop XRF, I believe you'd be able to detect a lot more of these features that we can see using higher resolution techniques. So the final question I have remaining for this study is how far this zoning extends from the sulfide. So far we've So far we've looked at the binary case of pyroxenes that exist basically right next to sulfide, and pyroxenes that exist in barren intrusions. So for this to be useful, we need to know how far away from the sulfide through the conduit that these zonings extend. So that's it from me. Thank you everyone for listening, and thank you for everyone who provided samples and technical expertise. This study was recently published in an open access journal article, so if you got that little QR code on the screen, it'll take you to the paper and you can read about it a little bit more. And if you have any questions, please type them in the chat and we'll get to them later. Thank you.